Okay, guys, so our last part of, I guess, new content for esters is going to be the hydrolysis of esters. So this is a new kind of reaction. It's just the opposite of the esterification reaction. So hydrolysis of esters is hydro, kind of like water hydration, but a hydrolysis is the esters breaking into its components. There are two different versions of this reaction that we will be learning, the acidic and the basic versions. So an acidic hydrolysis of esters is going to be the exact reverse of esterification. So we had an equilibrium process with an esterification. So it's the same exact thing. You have acid and heat, and it's going to do the opposite. So if we had started with an ester and water, we would then form a carboxylic acid and the corresponding alcohol. So again, in this reaction, we're going to just play flip-flop with the partners. So the carboxylic acid type thing and the alcohol type thing are going to swap places. So let's use orange, why not? So I'm going to take these two components and flip-flop their places. So then we have our carboxylic acid and we have our alcohol. So you can see that there are the green components were all together at first, and now they're broken up, and we put a carboxylic acid, and then we have our alcohol as well. So that's how it works. It's just the exact opposite. So let's do a practice one. So this is the molecule of aspirin. So the medicine, pain reliever medicine slash technically, what is it? A heart attack, something with heart attacks, right? I don't know. So when we do this reaction, we have this ester here. So it's drawn in a little bit of a different way. Let's circle the part that we're switching. So here is our ester. So we're going to be switching. This is where our alcohol comes off. So those are the two components that are switching. So I'm going to have here my alcohol. This is technically called a molecule called salicylic acid. So those of you who used salicylic acid acne medicine, that is the structure of salicylic acid. Oh, I drew the wrong color oxygen. I'm sorry. Swap those again. So in this particular example, I kind of flip-flopped the places of the carboxylic acid and the alcohol, but you can see the same overall process happens, and it's kind of like a search to find where you're going to be breaking, because it's not always going to be drawn in the exact same orientation. So this reaction also shows that because aspirin has an ester in it, if aspirin is stored in a warm, moist environment, that it could equilibrate to its alcohol and carboxylic acid version. It will eventually smell like vinegar. So this stuff right here, acetic acid, is the same thing as what's in vinegar. So if you have a really old bottle of aspirin and it starts smelling like vinegar, it's because there's salicylic acid and vinegar inside it. It's decomposing. You might want to get rid of it. I don't think it'd hurt you. No, it won't hurt you, but it's probably not very effective. That's okay. So we had our acidic hydrolysis of esters, which was the exact reverse of our esterification. Now we have our basic hydrolysis of esters. This is not a reversible process overall. So you'll see I have reaction arrows here. They're not equilibrium arrows. They make one product. So we have an ester and a base. Typically that base is a hydroxide base, or like sodium hydroxide, potassium hydroxide, something like that. And we form the carboxylate salt. and the alcohol. So if you remember in carboxylic acids, if we put the carboxylic acid plus a base, you make a carboxylate salt, and that's all you have is carboxylate salt and water. But now, because we have a alcohol that's attached on that ester, instead of just making the water, we make the alcohol. So ethyl propionate here is going to break apart. So really, to be honest, we're just doing the same reaction again, right? We're just swapping the place of two different things. So I'm going to take these two and swap it with these two. That's all I'm going to do. Actually, it's not that hydrogen. Let's just circle the oxygens and show that the oxygens switch. So technically, the sodium is going to stay with the carboxylic acid because the acid is more acidic. So it's not like a full switch on this one. Technically is, but I'm going to swap that color real quick. So we have our oxygens are going to swap places. We make our carboxylate salt based off of whichever counter ion we have here. So in this case, we have sodium. And then we're going to have our alcohol. And that hydrogen is going to be on the alcohol. So in chemistry, things are more basic and more acidic. So in reality, that hydrogen does swap over to make the carboxylic acid and then a negatively charged alcohol. But because our alcohol is more basic, it wants the hydrogen more, so that alcohol is going to steal the hydrogen away. It's a little bit tricky in terms of what overall is flip-flopping, but overall you can remember you make the same thing, your carboxylic acid and your alcohol. However, now it's the carboxylate salt version because you have a base. You don't have enough hydrogen atoms to go around. An example of this base hydrolysis is it's also called saponification. So that's the fancy word used for the making of soap. So triglycerides, which are fats in our body and fats that we eat, when mixed with lye, which is a natural version of where you can get sodium hydroxide, does this basic hydrolysis of esters and makes molecules such as these. And this is what we use as soap. So it has a hydrophobic portion. So typically, this is a lot shorter than it really should be. Typically, these are really, really long carbon chains. Just it could be saturated or unsaturated, but typically saturated carbon chains, and they're hydrophobic. So they dissolve other organic things. So things like grease on our body, organic things, and that part of the soap molecule dissolves that. Whereas the carboxylate salt part is a hydrophilic portion, and it interacts with water. So that's a more polar portion, and we have a hydrophobic, which is a more non-polar portion. So you have a polar and a non-polar portion all in one spot. It makes things called micelles, which is like kind of little bubbles to trap the organic-y things, or like the greasy things, away from the water. So that's kind of the short version of how soap works. Yeah. So our last video for this lecture is going to be some practice of hydrolysis reactions. So I'll see you guys there.